Hi everyone. Today I'll be talking about how we used Kafka to solve food wastage for a population of 1 billion folks. My name is Tejas Chopra and I am from Netflix. So the agenda of the conversation is as follows. I'll go over a brief introduction about myself. We'll go over exactly what the problem space was, define some of the requirements and how we ideated a solution, some of the design choices that were made along the way, including the choice of Kafka, and how using agile practices and designing iteratively, we were able to solve the problem. Finally, there'll be some results and takeaways. And this is a picture here of a very typical retail store in India that provides food grains and food and other basic cosmetics. This category is called the FMCG, which is fast moving consumer goods category. In the US, you have big stores such as Target and Macy's where you can do all this shopping. But in India, you have millions of such retail stores that are littered around the country. And that is the domain that we were trying to solve the problem for. So, a brief introduction about myself. Um, my name is Tejas Chopra. I started my journey in the year 2010 when I came to the US. I got a master's degree in electrical and computer engineering from Carnegie Mellon University with a specialization in computer systems. In the year 2012 to 2016, I was working at companies such as Apple and Samsung, where again I was working on distributed systems. In 2016, I joined a startup as the first engineering hire. And the idea was for me to build a marketplace like Amazon for fast moving consumer goods. And I'll get into what that entails. Um, at the very core, it is building software for the masses. In the year 2017, between 2017 and 2019, I joined a company, a startup called Datrium, where I was working on distributed file systems, storage, and replication. And then I joined Box, which is like Dropbox, but for enterprises, where again I was working on cloud storage. Finally, in 2020, I joined Netflix, where I work with the data storage platform team. And what I do is I provide microservices, infrastructure solutions, and storage solutions to allow exabyte scale data and billions of assets that are managed by Netflix studios and streaming platforms. Now, let us get into what exactly was the problem that I was trying to solve here. Uh, the problem space that I was trying to attack was the fast moving consumer goods. These are packaged goods, beverages, food items, cosmetics. Like I said, in India, you will find towns and cities that are littered with millions of these mom and pop shops. And they are very small and medium enterprises compared to the Macy's Targets in the US. The market cap for this industry is $50 billion per year. In the traditional sense, for this marketplace, the buyers are retail shop owners and the sellers are wholesale traders. So we wanted to create a platform where sellers and buyers can come together and do trade. And the goal was that by doing this, we were wanting to attack the wastage of food. So we wanted to avoid food wastage. As you can see, the number of wholesale traders and retail shop owners is very skewed. And the problem was that there was a lot of food wastage because of this skew. The food wastage was estimated to be around 70 tons per year. And there are several reasons for this. Firstly, the last mile delivery, that is getting the food to the retail shop, was actually very untimely, and it results in wastage of perishable items. Second, there is no feedback mechanism from the buyer, the actual consumer of the food, to the retail shop owner, to the seller. So there is no feedback loop to complete, and the end users of the product have no way to convey this information to the actual creator of the product. There is no good way of maintaining a catalog of items in a store. So a lot of times, these stores just have rely on memory to know what items are present in the store, and that may result in a lot of perishable items just going to waste. And finally, there are deeply entrenched relationships between buyers and sellers. So buyers do not have a means to explore other sellers and maybe seek better offers or faster service. So what if we could prevent this food loss? What if we can, like Amazon, create a marketplace for fast moving consumer goods, which does not exist today for small and medium enterprises in India, and which has wholesale traders as the sellers on one end and retail shop owners as the buyers? What this will do is it will give buyers a choice and sellers a platform to expand to other buyers. Choice is always good. It will help uncover better deals, timely deliveries, and a better user experience. The feedback mechanism can be integrated into the product. and users can have the ability to search for offers. To remove the issues with last mile delivery, shipping would be handled by us. So we will handle the shipping. And since this industry will almost always have bulk orders in a transaction, the shipping costs will get amortized very well across the orders. We are attacking a domain where the users are not very tech savvy. So it was important to build an empathetic user experience from the ground up. And this is something that I focused on. And technologies such as Kafka, Elasticsearch, DynamoDB, AWS, all of these came together and were critical parts of our journey. This is a picture of how a retail store looks or a wholesale store looks like back in India. As you can see, it is a deeply fragmented market. And there is really no way in which they can keep track of all of the things that are there in a particular store. And this is the problem that we were trying to, attack and solve. Now, there are several challenges when you think about creating a technology for people that are not very tech savvy. Firstly, our population had never used a smartphone, so they had used feature phones. They were not very well versed with how smartphones work and how an Android app would work, all of that. This industry works on extremely thin margins, and so we needed software that cannot drain the battery life. And so designing architectures that are cognizant of the amount of battery, CPU, and memory is very critical. People were not very well versed with English. English was not the first language. So products that had text written in English, we had to be mindful of localizing that for local languages so that our buyers are able to search, browse, and then choose products. Concepts of a cart, order tracking, and history are generally known to people that use Amazon and other marketplace apps, but are not known to folks that have never even seen them. So we had to educate our users about that. And there were a bunch of others. A good example is product images. Uh, Generally, when we are looking at Android or at Amazon, we care about a lot of attributes of the product that we want to buy. So we read a lot of text about the product. But in this industry, the sellers and the buyers rely a lot on the image itself and not so much on what the attributes are. So showing bigger images was again another learning that I got after talking and interacting with people. The next stage, once you've defined what are some of the challenges, is to define the requirements. Uh, when you think of a marketplace with buyers and sellers, there are some table stakes for a marketplace. First is the ability to search for products, get their relevant information, images, etc. Having an order management system with cart or order history or an ability to place orders and track orders. Authentication, having some form of OTP or notification during login or use. Associating offers with products that have been bought. And this is actually provided by the seller. So ability to sift through orders. And finally, a platform for the sellers, which are on the other side of the table. That will be a platform or an interface to ingest products, view orders, track shipments, generate invoices, etc. So given that we had this list of requirements, here are some of the design choices that we made. Firstly, we decided to go cloud native. So we used cloud services on AWS. Cloud provides scale, ease of manageability, pay per use, and is ideal for bootstrapping an idea. DynamoDB, we leveraged DynamoDB NoSQL database for our products, orders, notifications, shipments, etc. The data that we were getting was unstructured initially, and we wanted to use DynamoDB because DynamoDB inherently back in 2016 had streams ability. So it had change data capture, which meant that any row or anything that was added to the table or changed in the table would generate an event. And you can have downstream services that can consume that event and be processed. So and that's where we've used Kafka. Kafka was used for initially we started off with Kinesis, and then we realized some problems with Kinesis, so we moved to Kafka for event handling and async processing that would populate Elasticsearch and other tables in the downstream. So we'll focus a lot on this during our conversation now. And finally, we had Redshift. Redshift was a way to capture metrics and get customer insights. It's a data warehouse on cloud. And what, for example, metrics such as what are the products that users are adding to their cart but not ordering? What products get ordered more during the particular season? What products get ordered together? So this kind of insight is then provided to the sellers because that helps the sellers procure items in advance. So this is a data analytics layer that we built on top of our platform that can be leveraged, that was being leveraged by the sellers. Uh, Whenever you're architecting any solution, what is important is to think very deep about the solution. But when it comes to coding or writing software, design iteratively and write the code iteratively, use agile practices and get constant feedback. This is what I aim to do in this process. So the first challenge was to understand if there is a product market fit for this particular technology. And so the pilot was very interesting. It was just a simple SMS based solution. So because users were very well versed with SMS, they had feature phones. So we thought this is a great way to enter the market. In the SMS based solution, the SMS would contain a list of all the products that are available and their details, and the users would actually manually type and respond with the order. So you had buyers and sellers. They would interact with the cloud by using an API gateway, and we had a Lambda. The Lambda's job was to generate an SMS every morning and send it to the different users. And the Lambda was generating this SMS from information that is stored in DynamoDB tables. This information was again backed by S3 as well. And this required human vetting of responses and confirmations. So the backend was very simple. Like I said, sellers would upload an Excel with product information, price, and quantity available in DynamoDB. So that's how the product ingestion would work, and Lambdas would be invoked to send the SMS. Every evening, a human would create the Excel with order information and mutate the DynamoDB table. The conclusion, this provided a lot of learnings to us. One is Lambda worked great for time delivery of messages. Human vetting is painful. It must be replaced by programs. This approach is very rigid. There are no offers, no real-time quantity updates. And just by using the simple, very basic uh, architecture, we saw a huge surge in orders. We were doing more than $500 revenue per day. So then we realized that there is a product market fit. So we went with iterative development part one, which is invoking a Lambda on order placement. So if you see what we did in this particular iteration is we split the Android app users from the seller portal. So the seller APIs were different and the app APIs were different. We interact with a single API gateway. Seller portal APIs were implemented using a microservice on EC2 machines. And for the users, they would actually, whenever an order request would come in to our service, we would invoke a Lambda. The Lambda was invoked on order placement, and this would then go and mutate the DynamoDB tables as it was doing earlier. Product images were again stored on S3. This was a really quick development. It works great for less than 500 orders per day. And the problems were that it only works for single orders because we did not have any state management or cart at this point. So users would typically just see a list of products, and when they like to place an order, they would just swipe right and we would place an order for that product. Uh, Lambda has a slow warm-up time, so order placement was actually very slow. And we had realized that we had to replace the Lambda by an actual service. So we replaced that. That is when we removed all the Lambdas from our system for the initial flow. We replaced the Lambda. We created a monolithic service for buyers and for sellers. For buyers, this service was interacting with products, order management system, notification, and authentication. For sellers, it was dealing with product ingestion, offer ingestion, and invoice generation. The framework we used to create these microservices was Drop Wizard framework, and I'll get into that. At this point, there is no browse or search capability that we provided. The users would scroll down the app to find a product, swipe right to place an order. Also, we did not have any localization, and we did not get into any relationship modeling. So in FMCG category, there are relationships between products, brands, manufacturers, product verticals, and I'll get into the complexities that arise because of those. So all of those were not there, and that's why this was a very basic solution that we provided. Finally, we split our monolithic service into microservices. And that's where we started introducing Kinesis and Kafka as well. Monolithic services are difficult to scale, modify, test, and release. They deal with multiple databases, and there's a mixing of business logic, no clear separation of concerns, and no fault domains. So if something goes wrong, the entire service would go down. Uh, so we've split the monolithic service. We had product as one, order and cart management as another, notifications as another, and invoice as another. Note that we were very mindful of not having too many microservices. So typically, you can split a monolithic service into microservices in many ways. And one way to think of it is, every table should have its own microservice or CRUD APIs around it. But that's a very simplistic model. The problem with that approach is that when a request comes in from the client, and let's say you have to look at multiple tables, you will then end up calling multiple microservices. And each microservice call is an added latency. So what you want is to bring services or bring notions that live and die together into a single microservice. So in this case, for example, order management and cart management was a single microservice and not multiple microservices. The other important part is that earlier we used to only put information in the DynamoDB. Now we wanted that information to be consumed by downstream services, and that's where we used Kafka. And initially we started off by using Kinesis, but then we moved to Kafka, and we managed the Kafka clusters in AWS. And the goal of this was that whenever any table was mutated in DynamoDB, it would generate an event. We would consume that event and then forward this event to other consumers, such as Elasticsearch Indexer, Redshift Indexer, and Catalog Indexer. Now, the job of these three indexers is very interesting. So the Catalog Indexer would be used for sellers whenever they ingest a new product for that product to show up on the Android app. So product being ingested or product image being changed would go and make a change in the DynamoDB table. That event would be consumed by Kafka, and it would be forwarded to, or it will be processed using a consumer of Kafka, and it will then make the change in the S3 bucket and will be reflected on the user's app. The other one was Redshift Indexer. Like I said, we wanted observability and metrics to be a first-class citizen of our architecture. So Redshift was the data warehouse of choice. And we wrote a Kafka consumer that would consume the appropriate events, such as clicking an image or scrolling, all of these events, and make changes in the DynamoDB table, which would then be picked up by Kafka and processed by this indexer to put into Redshift clusters. The third one was Elasticsearch. So at some point, we wanted to provide users the ability to search and browse content. So on product changes, for example, ingesting a new product, which would mean that if the user is searching for all products under a brand, that product should show up. So appropriate Elasticsearch indexers or indexes had to change and be updated for it to be reflecting on the app. And that's the job of the Elasticsearch indexer. I said that we use Dropwizard for cloud native microservices. So Dropwizard is nothing but a framework. It's a collection of different types of softwares. Jackson, Jetty, Jersey. Jetty is an HTTP server inside the main method. Jersey maps the REST requests to Java objects, and Jackson is used for JSON serialization and deserialization. It's very simple to write a simple microservice with Dropwizard. All you have to do is create a resource class, register the resource, and then implement different methods. So in this case, let's say we wanted to call Hello World API endpoint, and we had to pass it a name query parameter, and you wanted to get some string as a result. So this is how this would produce a JSON type of content, and it's very simple enough to code up. We could have used Spring Boot as well, but Dropwizard was a choice that I picked, but Spring Boot could easily replace this. Dependency injection in Spring Boot comes built in with it. So the lines of code gets reduced significantly if you use Spring Boot compared to Dropwizard. So that is something that you might want to keep in mind when designing microservices. like I said, in this particular market, FMCG, um, it's very important to understand relationships between products, and why we needed something like Kafka to process a lot of these events and power our downstream services. Excuse me. When you look at things around you, for example, your iPhone, you know that the manufacturer is Apple, the brand is iPhone, the product vertical is smartphones, product line is iPhone 12, and the product itself is iPhone 12 with its IMEA number. For fast-moving consumer goods, these attributes are not always clearly spelled out. For example, if you look at this image is for Procter and Gamble products. The product verticals are baby, feminine care, family, fabric. The product lines are diapers, kitchen towels, and the brands are Tide, Ariel. Finally, the products are uh, Bounty paper towels, 33% extra. So as you can imagine, for a lot of food related items, the lines and relationships between manufacturers, product verticals, product lines, and brands are very thin. In order to give users the ability to search any product, there needs to be a way to get to a product. Our biggest challenge was because the relationships are very dynamic in nature. How do we build a backend store to serve the complex nature of these queries? We need the ability to search by brand and manufacturer, for example, and these are sample REST queries. So we wanted all products that belong to a particular manufacturer and a brand, all products that belong to product vertical, and all products that belong to product line and brand. And this is where Elasticsearch actually came to our rescue. So using Kafka and Elasticsearch, you can build an index and relationships that can help serve complex queries with extremely low latency. You can get features such as autocomplete right off the bat. And this is something that I leveraged a lot with our customers. So at this point, the state of the app was as follows. The buyer app had product search and browse. Buyers could place objects in a cart and order. And there was an order management system that generated shipments. The buyers could also view their previous order history. On the seller platform, we had the ability to ingest new products, update quantities, and they would be reflected on the app using Kafka. Uh, Sellers could update their offers, and again, they updating the offers would again reflect on the app and also update the Redshift indexers using Kafka. Sellers could get orders that are placed by the buyers, generate invoices and shipments. Finally, some results and takeaways from this particular experience that I had. There are a bunch of technical learnings for me. Firstly, DynamoDB is not the best database for relationships. The way I modeled relationships was that every time a product was ingested, uh, the product table had brand, manufacturer, product vertical as foreign keys. So a product being ingested would update the brand, would carry the brand information, and that would go to Kafka. Kafka event would be processed. And in Elasticsearch, what we had was an indexer that had a brand and a list of all products under it. So whenever a product gets ingested, from the brand key, we would go figure out the appropriate index in Elasticsearch and then insert the details of this product in the umbrella of brand. That way, whenever the user's application would query for all the products under a brand, we would have the result quickly shown using Elasticsearch. Um, so we could have used a graph database. We should have used a graph database like Amazon Neptune or Neo4j. This would can still be backed by DynamoDB. And the reason we would want to do that is because we still wanted to leverage the change data capture that comes out of the box for DynamoDB. Um, so Kinesis was not a good choice because Kafka allows faster retrieve of data and it stores data for longer. Kinesis is a default of 7 days. Kafka you can configure. Kafka also has great connectors for DynamoDB. It has great connectors for Redshift and Elasticsearch. So it is very easy to integrate in cloud environments. The other thing to note is that in 2016, when I started on this journey, Kafka clusters on AWS were not really well supported as much as the Kinesis that came built in. So a lot of time was spent in trying to debug a lot of issues on these EC2 machines or that were hosting the Kafka code for us. Also, Kafka comes with Zookeeper support and other things that you have to be mindful of when you're designing systems around it. Um, the third learning was that in this process, I did not use the containerization. So using Kubernetes and Docker for rolling deployments is the norm if you want to do any cloud deployments today. Um, so having like CI/CD pipelines, continuous integration and continuous delivery pipelines that can help trigger jobs on a check-in, and using a tool like Spinnaker, which is open source by Netflix, to for deployment and monitoring is something that is a table stake for developing any app on the cloud. Um, Also, I did not explore using service mesh. So what service mesh does is that when you have a bunch of microservices and they're talking to each other, service mesh makes the framework in which how microservices can communicate to each other. It allows you to listen on a lot of the calls, get some analysis on the amount of data being shared between microservices, and also provides insights into if something goes wrong, you can easily pinpoint which microservice went down. So it provides a call stack in some forms. And this is especially useful when you have a bunch of microservices that are asynchronous in nature or they are talking to each other a lot. Some of the product learnings were also very interesting for me. So I realized very quickly that even though I had cart, uh, the users were not using cart a lot because they did not understand the idea of a cart. So for them, placing an order by swiping was still a better user experience than placing an order in a cart and then waiting till the end of the day to place the order, because they will fulfill orders as the items get sold from their stores. So what I did was I removed, and every single time they place an order in a cart, that would incur a cost of shipping. So they would have multiple orders during the day. I needed a way to combine all these separate orders into a single order so that they can save shipping costs. And that I implemented using virtual cart. So a virtual cart was nothing but all the orders during the day would be single orders. At the end of the day, I would just create a virtual cart on the backend that would place all these orders into that cart. So that saved shipment cost by 27% for my customers. The other is an increase in orders due to enhanced searchability. So like I said, there are data gaps in product information. Products have missing manufacturers, missing product lines, and product verticals. So I invested in doing a research per product to ingest appropriate values that were driven by customer interactions. That led to an enhanced connection between products and enhanced searchability, and thereby also increased the orders by 24%. Finally, observability and metrics was a first-class citizen in this architecture. So I invested in building a Redshift data warehouse to gather insights such as clicks, browse, orders, search. That led to an increase by 34% in orders. It helped determine the seasonality of orders. It gave an insight into customer pattern, and it enabled our sellers to procure items in advance for fulfillment. However, what it also led to was an explosion in costs. So we went from $500 per month to like $4,500 per month within a span of 3 months by just having more metrics. Finally, the results. The number of wholesale traders on our app, which are the sellers, went from 1 to 7 within 6 months. The retail shop owners went from 10 to 400. The insights that we were capturing went from 7,000 insights per second to like 780,000 insights per second. Our revenue grew from $200 per day to roughly $8,000 per day. And finally, it led to an efficiency improvement in saving the wastage of food by 27%. So in this journey, the takeaways that I had were: one, you build software for the customer, and you need to show empathy towards the customer, understanding the customer behavior, the customer pattern, understanding their use of technology is very critical in designing solutions. So you cannot apply the tried and tested ways of how different industries work into a new territory. You have to get the best practices of that industry and keep the curiosity, the interactions going with the customer so that you can develop a solution catered to the customer. More code is more bugs. So there's a common adage that every 100 lines of code, there's a bug. So the best way to reduce bugs is to write less code to do the same task. So ability to write simple, lucid, performant code is very critical when designing systems that scale. As systems scale, things will fail. So what you need to design for is the way to fail safe. For example, if you have to choose between a product image and an order management system, always give more like weightage to designing a fail-safe order management system, because once an order is placed, a customer really expects that order to be fulfilled. Even if one of the 5 images does not show up, that's okay. So what you need to do is, when you're designing systems, be mindful of the SLAs for different parts of your architecture and design around it. Um, you must take care to never lose customer data. Be mindful of the performance of your application on smartphones. So in our case, we wanted to reduce the battery life consumption, which meant that we wanted to reduce the CPU usage and the networking cost it takes to reach out to cloud and fetch data. And to do that, we would use caching strategies a lot. But if you cache everything, your memory usage will bloat up. So we employed techniques such as compression and deduplication to reduce the footprint of data, not only on the user's device, but also on cloud. And that really helped save battery life. Invest in learning about the business. So one thing as engineers we tend to do is, we tend to get a problem statement from business and we tend to focus on the problem statement. So we get very deep into trying to solve the problem. But sometimes it helps to, get out of our comfort zone and directly talk to the customers as well. And as an engineer, you can think of technology and technical solutions that the business may not be very aware of. And so that can help bridge the gap uh, bit for the user to reach to the next level, and for them to get ease of releasing some amount of pain, or easing some amount of pain that they have. For example, in our case, one of our problems was that our users did not have a catalog or a way to know what products are there in their store. Uh, Now it's very easy to build on top of order history, because if you have a history of all the orders, you kind of know how much quantity of a particular item is and what items there are. So we just built that software and we provided it to them free of cost, because that was tangential to our app, but something that we felt could ease the pain for the users. Data is gold. So when you're designing systems, invest in gathering metrics and insights from data right away. And this cannot be an afterthought. It has to be a part of the initial architecture. Cloud costs spiral out of hand. So you have to design intelligently for the cloud. Cloud is a very weird beast, because it actually, when you start small, you don't realize the pains, but as you scale, cloud costs exponentially grow. So when you're designing systems, you should be mindful of the services that you're using and do not be locked into a particular cloud vendor. Always design generic services that are multi-cloud and hybrid in nature. That's my time. Thank you so much.